Okay, yeah, the topic is about something relevant to non-crossing partition, but it's slightly different, but we will see what's going on. Okay. So, and thanks to Beyond, so it's already covered all of this. So I just quickly to go over that. So when we have a non-commutative probability space, it means that we have a unitary algebra come with a linear function of sending 1 to 1. And what's the freeness? It's already covered. Yeah, so I just skip. And also what's the free cumulant? Just over here, my notation is using kappa instead of the R. Okay. Since R will be different notation in my talk. Okay. So just quickly review those definitions. And also the important thing is usually when we try to understanding the probability distribution, we try to using the moment to describe him. Since we have something called a Kalman condition, it's guaranteed that, okay, the moment can be describing for the distribution. In many cases, of course, it's not for all the distribution. The important thing is moment can be used into describing the distribution in many cases, and but moment and the cumulant have some really good relation. So as long as you know the cumulant relation, it's enough to determine the distribution. Okay, so it's moment cumulant formula, and also about the transform. Okay, so if you try to transfer the first sentence to the second one, the moment condition and the cumulant condition can be understanding as the, if you're given a transform, here is Cauchy transform. You can see it's the power series is, formal power series is describing by moments. And let's corresponding something called R transform, which is the, here I'm using G inverse instead of K in Beyond's talk, okay. So the G inverse is a composition inverse, okay. So R transform actually is considered as a G inverse minus 1 over Z, and it's a formal power series. And you can see the relation between G and R. The G is describing by moment, and R is describing by cumulants. Okay, and the important thing by Steiger in 1994, the freeness can be understanding as eventual missing cumulant. It can be characterized by this property, and of course then the good result is, if you want to understanding the law for A plus B, yeah, then we know the A plus B, the cumulant for A plus B can be it's multilinear, so you can return by several terms. But only the first two terms, the only A and the B will survive, and all the miss will be killed. Okay. So if you transfer to a language for transform, will be RA plus B equal to RA plus RB. Okay. But here it's all about addition. Now this talk is focused on the product of two free random variables. So let's starting by a notation called S transform. So for S transform, when you're given based on if you have a non-commutative probability space, you given element, we assume a phi is non-zero. Then the S transform is divided by the following way, where SA is divided by 1 plus ZA over Z times the N inverse, where the N inverse is N is a moment generating function. Okay. And its important result is such S transform can be used to calculate the log over A times B, okay, by the following formula. SAB is equal to SA times SB. And now the question is, if you have two elements, A and B are free, we know we have R transform. It's perfectly to describing the convolution, addition convolution, additive convolution. And this one can be understanding as using a cumulant, and which is have such a relation. But how about the product case? This is a thing in this question, and actually it's done by in Dykema in 2007, and also later on there are several foreign work by Mihai, Basnek, and Nika, and so on. And but they consider not S transform, they consider the reciprocal of S transform, and where we will see actually the reciprocal of transform we call the T transform. It can be understanding as something the Tn is something we call the T coefficient, and the relation is also like the addition case. The T coefficient can be used to study the moment. But here you can see there's a different notation. It's NCL. We will say what's this later. Okay. Just before we jump to the NCL, let's try to figure out why we consider reciprocal instead of the S. So maybe give some idea. So let's sound like a well-known result. If you have two formal power series, and if they have such a relation, G and F have such a relation, then the coefficient S can be understood as such formula based on the pi of the pi is belong the non-crossing partition. Okay, so based on this one, actually here it gives you a flavor why it's work. So now if you consider the RA, now I try to simplify, make it easier to understand. So the phi, if you consider it's 1, since we consider non-zero, so you always can do normalized dividing. So RA is this one, and based on like a known result, the M and R have such a relation. And based on this relation, the S can be rewriting as this form, where you can further rewriting as this way. And if you set in the F by this one, which will give you a formal power series. The G, if you consider this one, it gives you another one based on the K, here I call T. Then S, F, and the G will satisfy this relation, where we'll tell you the kappa can be written understanding, so the free Kuhlmann can be understanding as this way. Okay. Let's give you the idea. Okay. But now here you can see we consider only one variable case. It's all the same, it's A. But let's try to consider more general one. So now let's start in the non-crossing linked partition. Okay. First, it's a first notation is if you're given a subset of n from 1 to n, we call they are nearly disjoint if it satisfies the following property. Yeah. First, if we don't assume they are disjoint, so they can have some common element. If I is belong to E intersection F, then I must be the minima of E, or I must be the minima of F. And they also needs if I belong to E, minima of E, then the size of E needs to be bigger than 1. Okay, it's very abstract, but we can see some example. So you can see here, in this case, 1, 2, and 2, 3, they are nearly disjoint. And their tribute case, if they don't have common element, then this one is automatically true. So they are nearly disjoint too. And the case for n equal to 4. Yeah. 1, 2, and 2, 3, 4 are nearly disjoint. 1, 2, 4, and 2, 3, they are nearly disjoint. So if you're given a set of non-empty subset of M, we say pi is a non-crossing linked partition if it satisfies two conditions. First, it's non-crossing. Second, it's nearly disjoint. So you can see the non-crossing is just, if you consider non-crossing partition, it's non-crossing and a disjoint. But here we give some more space. They are nearly disjoint. And we're using this notation, NCL, to denoting the correlation of non-crossing linked partition. It's a little abstract, so let me give some example. Okay, so all the non-crossing linked partition for 3 elements is a following view. So you can see the 1, 2, 4, 5, 6 is exactly the 5 element for a non-crossing partition on 3 elements. But don't have one more. And if for the case, the n equal to 4, they have more, much more. And yeah, you can see it's much more, and so on. Good. Okay. So, and yeah, that's a notation. Then let's start to define what's the P coefficient, what we are looking for. So first, I'm introducing 2 notation. One is S. If you're given a non-crossing linked partition, then we say S pi is we consider the element belong to 1 up to m, where the k is not a minima for any block. Okay. And the second one, I just give collecting the point, the element, the random variable such that they are not centered. Okay. And then the T coefficient is defined by the following way. Okay. So the T coefficient, we consider Tn is a sequence, and such that it satisfies this condition. Oh, sorry. And here you can see we consider summing up all the possible non-crossing linked partition instead of a non-crossing partition, where the T pi is defined by the following. So we consider this one. This part is very standard, like one of the way we define the free cumulant, but we also part of the element which is belong to the S pi. Yeah. So here is a part we consider the element which is not the minima for any block. Then we consider part of that. Okay. And I just give an example. Okay. Pause for a minute. Okay. Yeah. So what's the benefit to consider this? So maybe here. Oh, sorry. There's one more notation. So here, if I given a sigma, I call it non-crossing. I given a non-crossing linked partition. Everything in this notation means I and G in a same relation. Means you always can buy a sequence of block such that I is in the first one and J is in the last one, where they are connecting to each other. Move on. Yeah. And we consider if for any non-crossing partition, we're using this notation means we're collecting all the possible non-crossing linked partitions satisfy this relation. Yeah. If I and J in the same block, in the sense of pi, is equivalent to this. But actually, we only care about the case pi is a whole partition, which means we only care about the case I4. And IN, and which means in the example of n equal to 4, we only care about those things. You can see like 1 and 4, you can link by these two. 1 is in the first one, but 4 is in the second one, but they are linked to each other. And 1 and 4, you can link by this way, and so on. Yeah. And the reason to consider this notation is by the following result. Okay. So this by the work by the Mihai Popa, yeah, in 2009. Yeah. So if you consider the given element A1 up to AN, we consider non-center element, then the cumulant can be described totally by the T coefficient, where the pi belong to this notation, block of IN. I don't know what's a better way to say. Okay. Yeah. So we have such nice formula. And this formula actually give you another nice way to calculate the freeness. Is the following. So if you say the AI are free, it's equivalent to the vanish of mixed T coefficient. Yeah, and you can see here is the multi-variable case. But if you back to the single variable case, the formula is getting simpler. It's just exactly this one. And this one is actually back to the remark I mentioned before. Okay, so yeah, so here until now is about the free probability. Now let's move on to the infinitesimal free. But before that, you can try to think about it. Okay, when we have a random matrix, self-adjoint random matrix, you consider expectation trace and it's converged to something in some abstract space. Okay, so we have some limiting law. If you want to calculate or we want to know more about the information of such random matrix, we might want to understand the correlation. So if you want to catch the correlation for the 1 over n correlation, then we move on to, we need one more state to describing that. Sorry, one more linear function to describing that. Then such abstract space we call the infinitesimal non-commutative probability space. And you can see it's nothing but you consider non-commutative probability space, and we adding one more linear functional. This linear functional is play the role for the 1 over n correlation. So we consider phi prime sending 1 to 0. And in such a space, we also curious about not only the moment under phi, we also curious about the moment under the phi prime. So we will have introducing another notation. It's called infinitesimal free. Yeah, it's a kind of like a generalized of the really independent. Okay, so you can see if you have some sub-algebra, unital sub-algebra, they are infinitesimal free if the all condition is the same as the free condition. And the first condition actually is tell you they are free. Second, they give you a rule to understanding what's the free point of the product of element. This one can be understanding as the following formula. And so guess what? Since for the freeness, we have something called free cumulant. So in this case, we also have something called infinitesimal free cumulant. Okay. So now you can see the kappa m point. We call it they are infinitesimal free cumulant. First, they are multilinear functional, but they also satisfy some looks like a moment cumulant formula. But you can see here it's subtle different. We have a notation called partial kappa pi, where partial kappa pi is divided by this way. Okay. When you given a pi, they have several of the block, and each time you choosing one, you replace the kappa by point, kappa point, and all the other you just keep the same, and you sum up all possible of them. It's called a partial kappa pi. So the important thing is this result also follow. It's infinitesimal free can be calculated by the valuation of missing cumulant and also the valuation of missing infinitesimal free cumulant. Okay. So it's by the work in February and Nika. Yeah. And now we want to say more. Now we know we have some coefficient, T coefficient for the free case. So we were looking for also the infinitesimal version of that. So before that, let's starting by, if you give an infinitesimal non-commutative property space, the infinitesimal S transform is given by this way. And where the n is the moment generating function, and the partial m is this is just replace the moments by phi prime instead of a phi. And then the partial t, the infinitesimal t transform is given by this way. So you can see actually this guy is, you just consider the formal derivative for the 1 over s. And based on this, we have some nice relation to understanding them. If x and the y are infinitesimal free, then the partial of sxy, the infinitesimal s transform, can be described by the following formula. It's just the product rule. And the same for the t coefficient, sorry, t transform. Yeah. Yeah. So let's label of a transform. And if you want to compute in a concrete example, using those transform, it's pretty hard since you can see the formula is like this, formula like this. And so it's not too easy to compute. So then I move on to introducing the infinitesimal t coefficient. It's really very helpful. Okay. So the notation is the same. A tilde, A bar means we consider all the non-vanish first moment, and the S pi is the same. Okay. So infinitesimal t coefficient, Tn prime, is given by the following formula. But this one is little more difficult. It's summed up by these two terms. So you can understanding as actually it's just a derivative for the original formula, the formal derivative for original formula. And guess what? They have also nice relation. The infinitesimal free cumulant also can be calculated by the infinitesimal t coefficient. And furthermore, infinitesimal free also equivalent to the valuation means t coefficient and infinitesimal t coefficient. Yes. Go back. One more. This one. Yes. It's much more complicated. Yeah, we have updated the value version. Okay, so then for the single variable case is also easier to understanding by the formula. And okay, then let's abstract theorem. How about the application for that? So let's okay. So if you consider the application to random matrix theory, so let's maybe starting by a complex Wishart matrix. Okay, okay, it's given by this way. And if we further assume that n over m, which is converted to something c, usually that's a standard assumption, but if we assume further that m minus nc converted to another quantity is called c prime, then you know it's proved by the Jamie Mingo, is if you have two such random matrices, independent complex Wishart matrix, they will be asymptotically infinitesimal free. And furthermore, those those cumulants can be computing precisely. The kappa n is c and kappa n prime is c prime for all of m. So I forgot to mention the phi is given this way, it's standard way, and phi prime is catch the one-to-one correlation, so it's given by this one. So based on this one, we have this cumulant. We have kappa n and kappa n prime. Then based on, we can using this formula to understanding the t. So it can be proved that the Tn and the Tn prime is given by this way. Yeah, you can see it's very simple. Yeah, and this one is equivalent to saying what's the T transform and infinitesimal T transform. And furthermore, if you have two infinitesimal free variables and following where they are following the limiting law of the complex Wishart, then you also have a corresponding T and the partial, the infinitesimal T transform. Yeah. So this one is since the original way I computing is using the transform directly, and the formula is pretty a little ugly, and I didn't see any nice way to interpret that. This one is much simpler. And before the end, I try to mention one thing. If you go back to the way I define in the S transform, it's based on the fact that we assume that phi x is non-zero. Yeah. So we consider it's a non-vanishing mean to guarantee the n inverse exists. But how about the case if the mean is vanished? Yeah. And this one was considered by the Lauren and the Law in 2007. And based on this one, you will get not only one S transform, you will get a pair of S transform instead. Yeah. And then you also can get some result. Yeah. But the problem, there are further problems after that. The first question is, in this case, the phi y0, based on the Lorentz work, they will have two S transform. And so if you consider reciprocal, you have two T transform. And whether such T transform, their coefficient has also nice combinatorics formula, like non-crossing linked partition, still unknown. And yeah, and if you consider further, how about the case if you have two free variables where the both mean vanish? How about such case whether we also can have some nice combinatorics interpretation for that? Yeah, yeah. What I know is they still unknown. Yeah. So there are several things I still try to think about it. Yeah. Okay. That's all my talk. Thank you.